Right, today we're going to be covering paper 6, which is the alternative to practical. This is for physics, May-June 2017. It's paper code 0625/61, and this is for the Cambridge IGCSE.
Right, let's get it done.
Question 1. The class is investigating the stretching of a spring. Figure 1.1 shows the apparatus. Okay, so we get a spring just hanging off a clamp. We've got a meter rule next to it. It's a fairly okay setup. Right, on figure 1.1, measure the length L0. Record L0 in the table 1.1 at load L equals 0. So let's look at the table. Right, so it wants us to record L0 just here. There we are. So we fill that bit of the table out with the value that we get from measuring on the picture. Now, one of the things you'll find, of course, if you print out the paper and try and measure it, you'll probably get a different answer to the answer that they give you. The reason is that they'll print it out on their size paper. If you print it out on A4, you might get a different reading. If you print it out on letter size, which is what I used, then you'll get a different reading. When I measured it, I got 14 millimeters. But if you look at the back, you'll see it was 15 millimeters. That's what's required in the answer, and that's what you would get if you measured the length L0 from here to here using an actual exam paper in the way that's been printed out. So just be aware, for things like this where you measure or where you take a physical measurement from the paper, there's every chance it will come up slightly differently to the answers. Don't worry about it and just proceed on. So that gives us our value for the table, 15 millimeters. There we go. Of course I don't actually have to write millimeters in because that's at the side here. A2. Explain why L0 is not measured to point X on the spring. There we go. Why not measure it to point X? Well, the rings don't extend when the weight is added. The only thing that extends is the spring itself. Okay, so let's move on to part B. A student hangs a 1 Newton load from the spring. He records the new length L of the spring. He repeats the procedures using loads of 2, 3, 4 and 5 newtons, and the readings are shown below, so they've put everything in for you. Describe one precaution that you would take in order to obtain reliable readings. Well, you know what? Number one, very important, certainly one I always put down, is you would read it at 90 degrees. Oops. Another thing you could do to make it more accurate, use a set square. And I know I've had a few people over the years ask what a set square is. And a set square is one of those things that you get that you're never really sure what to do with whenever you buy these little geometry sets. The things that look like triangles. There we go. They look like that. And get a really nice accurate reading on both sides. You would take it, then you'd flip it upside down, measure it again. And what that does is it gives you a 90-degree angle. So it means that you know you've got a 90-degree angle, you're looking at it perpendicularly and you're getting the right reading. It's called a set square because a square obviously is a 90-degree angle. It's like a part of a square. Now part C. Plot a graph of L in millimeters on the y-axis against L in newtons on the x-axis. So L will be the length of the spring and large L will be the force in newtons. Yeah, there we go. It's already in the table. Now, one of the things you'll find out if you count these large sort of double squares, you'll find there are 8 of them. 8 up and 8 along. Okay, so let's look at the numbers that we have to work with. From here we're going from 0 to 5 newtons. What does that mean? Well, we may as well take one double square, 110 be 10 square, and let's just say that 1 Newton equals 10 little squares then. just one large double square. In case you're wondering why I tend to call them double squares, it's because normally when they do them, you see there's a slightly darker line here, more dark line here, and it's as if this is made up of two little squares of 5. There we go, like that. So I just tend to call that a double square. Let's just call it 10. 10 little squares. So we may as well use 10 little squares to be equal to 1 Newton. That makes sense. Okay, so we've got a good scale for it. First thing you want to do whenever you're doing a graph is look at the scales. Okay, next one. A little bit more tricky. We go from 15 to 25. That's a gap of 10 millimeters. So 10 millimeter gap, that's 25 minus 15. So 10 millimeters that I need to show up on the graph. I've got 8 of these big 10 long squares to work with. So maybe the best thing is to say that 10 squares is 2 millimeters. Then what I can do a jump. I can start from 15, so I can do a little asymptote on the axis. I can start from 15 and I can put up to 25. There we go, and that would be 5 squares. Sorry, that'd be a total of 6 squares because we start at 15 and we want to go up and see 25 as well. Alright, so let's look at how that's going to look. Do a little break in the axis there, and that's how you do a break in the axis. And we're going to start at 15, 17, 19, 21, keep going up, 23, 25. There we are. What I'm going to do, I'll just draw a line along there. There we go. And one of the key points whenever you're drawing a graph, label the axis. So this is L in millimeters. Here you go, as required. L in millimeters on the y-axis against the load in newtons on the x-axis. So the load in newtons, as we said, we'll start at 0 newtons here. Then we've got 1 newton, 2 newtons, 3 newtons, 4 newtons, 5 newtons. There we go. Except, of course, we don't need to write newtons on the graph. It's one of the reasons why it's so useful to label the axis. There we go. L in newtons. Now I know everything on that axis is in newtons. Okay, so now I can start labeling my points on the graph. What do I have? Well, 0 is 15 millimeters. So I can label that first. 1, 17 millimeters. 2 is slightly out, it's 20 millimeters for some reason. Probably just to see how well we do with drawing the line. 3 is, let's just come down so you can see that we're doing this at the right points. There we go. 3 is 21 newtons. Sorry, 3 newtons is 21 millimeters. There we are. 4 is 23 and 5 is 25, so we'll go up slightly for that. There we go. And what we'll do, we'll put in a line of best fit. What we can see is everything is beautifully on this line of best fit except for 1 point, and in that situation we just ignore that 1 point. We call it an outlier. So let's see what the next question is going to be. D. A student suggests that the length L of the spring is directly proportional to the load L. It's frustrating if you use 2 L's, isn't it? The length of the spring is directly proportional to the load. Okay, well, let's underline the key point here. Directly proportional, not proportional. Proportional means straight line, and it's a straight line fit, so that would be true, but directly proportional is different. Directly proportional means it goes through the origin, 0, 0. And if we look here, we can see that when the load is equal to 0, the extension is 15. So it's obviously not directly proportional. It is proportional, but not directly proportional. So if it's directly proportional, it has to travel through the origin. So let's just answer that question. So no, the line that's best fit does not travel through the origin, 0, 0. Use the results to predict the load L that would give you a length twice the value of L0. Ooh, show clearly how you obtained the answer. Well, let's see this. Maybe just start making a couple of points. So L0 is 15 millimeters. So twice the value of L0, 2L0, is 30 millimeters. The question is, when does it reach that value? Well, we've already got a bunch of information, haven't we? We've got 3, 4, 5, 1 through 5. So let's just continue that on. So L and L0, I'm just going to start 3, 4, 5. And I'm just copying this first bit from the table that we've been given. We're going to extend it on. This should be absolutely fine. Now we can see straight away that as the load increases, each newton gives an extra 2 millimeters in length. Alright, so 5, 6, 7, 8. Well, 6 will be 27 millimeters, 7 will be 29 millimeters, 8 will be 31. And we want to know when the value is 30 millimeters. And that looks to me like that's going to be 7.5. So load L equals 7.5 millimeters. Question 2. The class is investigating the refraction of light passing through a transparent block. A student is using optic pins to trace the paths of rays of light. Now these questions are interesting, and I'll tell you why. They're not hard, but oh my god, the way the question is worded is horrific. They always are. They're always the same thing. They're never tricky, but getting through the language is a pain. So we get a ray trace sheet. This student has drawn around a block. They've got a couple of things labelled P4, P3 and a picture of an eye. Alright, the block's labelled A, B, C, D. Nice and straightforward. So, part A. The first bit. Draw a normal at the centre of side AB. Label this line NL. Label the point E where it crosses AB. Label the point M where it crosses CD. I always wonder if they write these, if they chuckle as they write these questions, or if they feel a little bit ashamed that they don't make it more straightforward. The task should not be to confuse you with the use of horrific sentences. That's key points here. So we're drawing a normal at the centre of the side, AB. So at this side, along this side, at the centre, we're going to draw the normal line. And a couple of key points. We want to label it where it crosses AB and label it where it crosses CD. So that means it's going to cross both sides. And it's going to be in the centre. I'll do this as a bit of an approximation. So obviously I'm doing it on the computer. There we go. So I'm going to say that that is the centre. In the exam you should be measuring it. So let's draw a nice straight line here. There we go. Beautiful normal line. So label the line NL. N at one end, L at the other. I'm going to put N at the top because I think that just makes more sense to me. So N at one end, L at the other. Label the point E where it crosses AB and M where it crosses CD. So where it crosses AB, it wants me to label it E, and it wants me to label it M where it crosses CD. So that's all the first question's asked you to do, or the first part of the first question. Next, draw a line above AB to the left of the normal and at an angle of incidence of I equals 30 degrees to the normal. Label this line FE. So what it wants us to do here is draw a line at 30 degrees to the normal. Whenever you're drawing these lines, make them big and long. That's what they like to see. Alright. So we're expecting this. You should measure this obviously as you do it, because this angle here should be 30 degrees. Let's see what we're supposed to label it. So we've drawn a line to the left of the normal, that's right, angle of incidence 30 degrees to the normal. Label this line FE. There we go. So F and a point E is already labelled. That's really what tells you that they wanted to join the line. But that being said, you know, if you're unsure, it's more than likely that it's got to join that section of the line there. So they both meet at the line along AB. Okay, so let's just do a little check mark as we do it. So done. Yeah, we've done this section. In fact, let's check off the individual parts. Done, 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 done. And that takes us to the next bit. Label the position of two pins P1 and P2 placed a suitable distance apart on FE for accurate ray tracing. Alright, so it wants us to label a couple of pins here, and it wants them to be far apart. These pins are just the pins that if you stick them into the board, and go round about the eye level and line them up, then you'll see a nice path that a ray would take. That's all that these pins are for. Okay, there we go. The student observes the images of P1 and P2 through side CD of the block, so the images of P1 and P2 appear one behind the other. So they're lining up. The two pins are in a line, they're lining up. He places two pins P3 and P4 behind his eye, between his eye and the block, so that P3, P4 and the images of P1 and P2 seen through the block appear behind each other. So the whole thing's form a line, and if you were to put your eye just here and look, you'd really only just see one pin, and the idea is that the other pins are hiding behind it. So you know it's all in a straight line. Label the position of two pins P1. Oh no, you've done that bit. Check that off. It's one of the reasons why you want to start checking these bits off. There's a lot of confusion in it. So, places two pins, and okay, so that's just saying that he's placed the pins there and nothing to do. Let's move on to the next bit. Draw a line joining positions P3 and P4, continue until the line meets the normal. Label this point K. Ooh, dear me, it goes on. And why wouldn't it? Because we're having lots of fun. There we go. Beautiful. Don't forget to label the point K, which is what they've asked for. So we can now put tick there. Record and measure the angle alpha between the line joining position P3 and P4 and the line KM. Alright, so I want you to measure this angle here using your protractor. And the value you should get there should be around about 30 degrees. Measure and record the length X between points M and K. Now when I did this and measured it out, I got 21 millimeters. Don't worry if your answer is different if you're running through it, because as I said before, whenever you're measuring something on these practical exams, there's a good chance you'll get a different measurement by a millimeter or two to the answer in the back. And the reason for that is that they print it specifically on their paper. You might be using A4, you might be using letter size, and it's coming out differently to the paper you'd get in the exam. So that's okay. You can expect a couple of millimeters difference or a couple of degrees difference, that's not a problem. And D, the student repeats the procedure with an angle of incidence I equals 50 degrees. His readings for alpha are shown below. We get 52 degrees and 19 millimeters. A student suggests that the angle alpha should always be equal to the angle of incidence I. That's very helpful of him. State whether the results support this suggestion. Justify your answer by reference to the values of alpha for I equals 30 degrees and I equals 50 degrees. Well, yes, it looks like the answer is, doesn't it? Here we have 30. Oh, you see that error? You get 5 seconds to figure out what that error is for the angle alpha. Here we go. Always check your units. That's why it's a good idea to read through afterwards and double check. Okay, so angle alpha equals 30 degrees, and that was also the angle going in. And here, angle of incidence equals 50 degrees. And the angle measured coming out is 52 degrees. They're pretty close to each other. So the statement really should be, yes, I think that alpha should always equal the angle of incidence I. And justification, because these are the same within the limits of experimental accuracy. Put down the numbers. So there we go. Yes, I think that alpha should always equal the incidence angle I. For justification, for I equals 30 degrees, alpha equals 30 degrees, and for I equals 50 degrees, alpha equals 52 degrees. These are the same within the limits of experimental accuracy. Now, suggest one precaution you could take with the experiment to obtain more reliable results. Well, number one, you could have a larger pin separation. That's one of the biggest things you have here. Another key point that you could have put instead is use the base of the pins. There's a few different things. The reason, of course, being the base of the pins is fixed. The top of the pins might be to the left or to the right, forward or backwards by a few millimeters. 3. The class is investigating the cooling of water. Figure 3.1 shows the apparatus. Alright, we have water, beaker, thermometer, all being held by a clamp stand. The thermometer shows the room temperature at the beginning of the experiment. Oh, record theta R, which is the room temperature. How do we know it's room temperature? Here it is, they've labelled it just there. Right, and that is a reading of 23 degrees Celsius. And remember units here. There's no units written down, so make sure you put down the units so that you get the marks. B. A student pours 200 centimeters cubed of hot water into the beaker. She measures the temperature theta of the hot water in the beaker. She immediately starts the stop clock. After 180 seconds, she measures the temperature theta of the hot water, and after 360 seconds, she measures the temperature theta of the hot water again. The results of the readings are shown in table 1.3. Right, part 1. Calculate the temperature fall delta theta 1 during the first 180 seconds. Alright, nice straightforward. All we need to do, the temperature fall is 85 degrees Celsius minus 74 degrees Celsius, which gives us a value of 11 degrees Celsius. And calculate the temperature fall delta theta 2 during the next 180 seconds. Well, that's just 74 degrees. Do it at the top here. 74 degrees Celsius minus 66 degrees Celsius, which of course will give us a value of 8 degrees Celsius. Interesting thing, if you're very used to the idea of doing the final reading minus the initial reading, which is always a good idea, to have 66 degrees Celsius minus 74 degrees Celsius, which will give you a value of negative 8 degrees Celsius. And the negative just tells you that it's a temperature fall. So it tells you the direction it's going in. Now, part 2. Suggest why the temperature change, the first temperature change, is different from the second temperature change. Well, the rate at which heat is being lost decreases as the temperature of the water decreases and approaches the room temperature. So the closer it gets to the room temperature, the less heat energy will be lost per second. There we go, so the rate of heat loss decreases as temperature decreases and approaches room temperature. C. Another student plans to investigate the factors affecting the difference between values of delta theta 1 and delta theta 2. Of course, delta just means change in temperature 1 and change in temperature 2. Suggest 2 changes that he could make to the procedure to obtain a larger value of this difference. Okay, well, you know what? Number 1, increase the surface area. Increase the surface area of the liquid. Another thing they could do, decrease the temperature of the room. Another possibility, think about if you've got a hot cup of tea, you blow over the surface. That would work as well. Blow air over the surface. I'm just writing this down because, well, we're on the question again, just to show it's not two answers, there's actually several. Other possibilities, why not use a metal beaker? D. The volume of water used in this experiment is measured using a measuring cylinder. Figure 3.3 shows a measuring cylinder. There we go. A, B, C and D are 4 possible lines of sight that could be used to read the volume of the water. Ooh, you want to use B here. Give 2 reasons why B should be used to obtain the most accurate reading. Well, the reason why you'd want to use B is because it uses the base of the meniscus, which is what you should be using, and also it's perpendicular to the surface. So it's perpendicular to the surface of the liquid. 4. The class is investigating the motion of a pendulum. Figure 4.1 shows the apparatus. A1. On figure 4.1, show clearly the length L of the pendulum. The length of the pendulum is actually given from the center point of the bob to the base of the clamp. So it's this area here. And that is the length L. Use figure 4.2 to explain how you would measure the length L accurately. You may draw on the diagram. Alright, so figure 4.2, here we go. This is the one we want to draw on to show how we're going to measure it. We've been given a meter rule and a set square. So, what we do, have the meter rule right up here and the set square we would use to make sure the reading is at 90 degrees. There we go. Label them. So we want to explain that as well, so that gives us a chance to get over our terrible drawing and put down a little bit of an explanation, make sure we get the marks. So first things first, measure from the bottom of the clamp to the centre of the bob. So now how do we do that? Well, we use the meter rule to line up with the bottom of the clamp and the set square to line up with the centre of the bob. So let's put that in. There we go, so measure from the bottom of the clamp to the centre of the bob, use the meter rule to line up with the bottom of the clamp and the set square to line up with the centre of the bob. Problem solved. Right. B. A student determines the period T of the pendulum. The period is the time taken for one complete oscillation. The student measures the time T for 20 oscillations. Time little t and periods big T. So figure 4.3 shows the little t, which is time for 20. Calculate the period T of the big pendulum. Alright, nice and straightforward. What we have here, just to calculate it out, is if T equals 20.22 seconds, then the big time period will be 20.22 seconds divided by 20, because the little t is 20 oscillations, so the time for one oscillation is just 1/20th of that. It's 1.011 seconds. So for a big time period, we're just going to put 1.01. Remember the units, seconds. 2. Explain how measuring the time for 20 oscillations rather than one oscillation helps the student to obtain a more reliable value for the period. Well, this is going to reduce the effect of the reaction time error by spreading it over 20 swings. Let's put that down. There we go. Reduces the effect of the reaction time error by spreading it over the 20 swings. C. A student wants to determine the value for the acceleration of free fall from his results. He needs the value of t squared to do this. Calculate t squared. Give your answer to a suitable number of significant figures and include the result. Alright. So calculate t squared. I'll be wanting to take that 1.011 seconds. I want to square it. There we are. 1.011 was the overall answer we got before we reduced it to the 3 significant figures, the 2 decimal places. So if I take that number and I square it, I'm going to get 1.022121. And that's way too many significant figures. So what I'm going to do is just change that to put 3 significant figures, 1.02. That's the number of significant figures I want on it. Okay, but now the units. I've got 1.011 seconds and I've squared it, so the units of this will just be seconds times seconds, it's seconds squared. There we go. So my final answer, 1.02 seconds squared. There we go. Question 5. A student is investigating whether the resistance of a wire depends on the material from which the wire is made. Resistance R is given by the equation R equals V over I. The following apparatus is available to the student. Ammeter, voltmeter, micrometer, screw gauge, power supply 0 to 3 volts, variable resistor, switch, connecting leads, wires of different materials. Plan an experiment to investigate whether the resistance of a wire depends on the material from which it is made. You should draw a diagram of the circuit that you would use to determine the resistance of each wire. Explain briefly how you would carry out the investigation, including the measurements you would take. State the key variables you would control. And finally, draw a suitable table with column headings to show how you would display your readings. You're not required to enter any readings in the table. Alright, let's look at that. Let's do our basic circuit for investigating the resistance of a wire. Our basic circuit, we've got a power supply here. And of course that's going to connect round in some way, here we go, to the wire being tested. We were given the equation R equals V over I, so we're going to need to measure V across our wire and I as well, the current. So we'll put our ammeter into the circuit here. Now a very important point is this, oops, if I leave a gap like this, it's wrong. Even though it's obvious what I'm doing, no gaps in circuits. Okay, very important that. Now, so I've got a wire connected in series with the ammeter, it's attached to a power supply. I need to take the voltage across that wire as well. There we go. There we are. Excellent. So, now let's talk about what we're going to want to do. Well, we're going to want to connect the circuit like that. We're going to want to make sure that the wires we have got the same length and they're as wide as each other. Same cross-sectional area. And that's because, of course, the resistance of a wire is proportional to the length and it's inversely proportional to the area. So we need to control both of those bits. They are our control variables. So we can use a micrometer to measure the area, and we probably need a meter rule to measure the length. Okay, so our control variables in terms of controlling the wire itself, we're going to control the length, we're going to control the cross-sectional area. The other thing we're going to want to control, so it's independent of the wires, is the voltage. So each wire is getting exposed to the same voltage. We're going to want to keep that current nice and low so the wire doesn't get hot. Alright, so let's start looking at that and let's try and explain that through. So first thing, connect the circuit as above, use the micrometer to ensure that the wires have the same diameter. That means they'll have the same cross-sectional area. The other thing we're going to want to do is control the length. So ensure the wires have the same length, either measure them against each other or use a meter rule. So ensure the wires have the same length, either you measure them against each other or use a meter rule. So that's two of our control variables. The last control variable we're going to want to use is the voltage. We want to keep the voltage nice and low. There we go. So measure the voltage and current for each wire and keep the voltage and current low to avoid heating due to the current. So our control variables are going to be the voltage, the length of the wire, and the cross-sectional area of the wire. Controlling the voltage lets us control the temperature. But we're not measuring the temperature of the wire, we're just making sure it's a low voltage, low current. So what we're going to record? Well, we're going to record the type of wire, the voltage in volts, the current in amps, and calculate the resistance R in ohms. Alright, so that shows everything that we're going to do and everything we're going to record. Now we want to make a couple of suggestions just to see how we're going to keep it as accurate as it can be. And what we're going to do is, well, repeat and take average of the readings. Always a classic. And I think just state again we're going to use a low current to keep the wire cold or cool, just to make sure that we're hammering home that point. And of course that's important because if the wire gets hot, the resistance changes. There we go. That's it. We are done. So I hope you enjoyed it. If you enjoyed it, feel free to like and subscribe. If you have anything that you'd like me to cover, just leave a note in the comment section below, and have a lovely day.